Hello, welcome to this lecture in which we are going to make an inventory of the different ways to bring air, heat and cold in the rooms of a building. All three are essential to a healthy and comfortable indoor environment. It is good to realize first that there are different traditions all over the world how to do that. Some of you may know only air systems, while others are familiar only with radiators and others only with room air conditioning. So, let's bring structure in all these things and make sure you get the full picture. Let's start with the transport of hygienic air. Hygienic air is the quantity of clean outdoor air that is needed to maintain a good indoor air quality. You have learned in other classes and courses that a minimum of 25 cubic meter per hour per person is needed, and that higher values are recommended between 36 and 50 cubic meter per hour per person. It is very important that this clean air is brought directly where people need it, which is in the building's rooms. As for the transport of air, ventilation systems can be divided into four types. The completely natural ones, through windows or opening in grills. You see here a section of a building with a corridor and rooms at both sides. Second, the systems with an exhaust ventilator pushing the air out of the building while the supply air comes naturally in. Third, the ones with mechanical supply where the air is pushed inside the building and then flows away through window openings and cracks. And fourth, the ones with mechanical supply and exhaust, generally equipped with a heat recovery heat exchanger. Only the two last types, the ones on the right, allow for centralized air handling. So, in three of these systems, pipes are needed to transport air. The more air is needed, the bigger the pipes. For an architect, it is extremely important to know already at the start of the design how big will be the pipes. He has to account for them in its spatial design and reserve enough space for it. So, as an indoor climate designer, one of the first things you'll have to do is to make a choice between one of these four systems and to estimate the size of the pipes, if any. That was for the hygienic air. Let's look now at the transport of heat and cold. Let's consider a room with its heating or cooling demand that you have learned to calculate in another course by making an energy balance accounting for the heat losses and gains by transmission, ventilation and infiltration, solar gains and internal heat gains. If the balance is negative, there is a deficit of heat and the room must be heated. Otherwise, it would become cold. See on the left. If the balance is positive, there is a surplus of heat and the room must be cooled, otherwise it would become hot. See on the right. Basically, there are three main ways of bringing heat and cold in a room. First, you can generate the heat and the cold in the room itself. There is therefore no need for transport. This would be the case if an electrical radiator or a stove are used in the room left or a room air conditioner like on the right. Very often, the equipment generating heat and cold is not placed in the room, but somewhere central in the building, like a home boiler is placed in the toilet or the attic. In office buildings, you see often big technical rooms on the roof where the boilers and the cooling machines are placed, like on the picture, meaning that we need some piping to bring the heat and the cold to the rooms, and we need to choose which fluid will be circulated in these pipes. Basically, we have the choice between only two solutions, air or water, which are abundant, cheap and harmless in case of leakage. How to choose between both? To be able to make a choice between water and air as transport fluid for heat and cold, we need to consider the size of the transport ducts. Let's start with closed system and consider heating. It works exactly the same for cooling. In a closed system, a fluid is heated by the heat generation system, a boiler for instance, and circulated through a pipe and a heat exchanger to the room. In the heat exchanger, the fluid gives its heat to the room, by which the room is heated and the fluid is cooled. The cold fluid goes back to the heat generation system and is heated again, and the cycle goes on. The quantity of heat needed by the room is Q heating, so that is the quantity of heat that the fluid must gain in the heat generation system. This heat can be expressed very simply by this equation, saying that Q heating is the density times the specific heat of the fluid times its volume flow rate times the temperature difference T in minus T out. Let's compare the properties of water and air. The specific heat of water is 4.18 kJ per kilogram Kelvin. Rho is 1000, so rho Cp is 4180. As for the air, Cp is 1 and rho is 1.2, so rho Cp is 1.2, quite a difference with water. This difference must be compensated by a much higher flow rate of air compared to water, if we want to bring the same quantity of heat. You see below that the volume flow rate of air must be 3483 times the one of water. What a difference! What does that mean for the size of the ducts? Well, the volume flow rate of a fluid can always be expressed as the product of the cross-sectional area of the pipe and the velocity of the fluid. So it is P times R squared times the velocity, where R is the radius of the pipe. Because of noise and pressure, it is better to limit the velocity in ducts. In a main air duct, the velocity will be around 10 meter per second. In a water pipe, it will be around 1 meter per second. So, by using these values in the equation above, we find that the radius of the air pipe should be 19 times the one of the water pipe. You see here how that is. In general, the water pipe leading from the boiler to the radiator has a diameter of about 2.5 centimeters. To transport the same quantity of heat with air, a pipe of diameter 36 centimeters is needed, which would look like this air pipe on the figure. And there is an additional thing to think of, and that is the size of the heat exchanger in the room itself. In a lecture about heat exchangers, you have learned that the surface area of the heat exchanger can be calculated with this formula, where T mean is the logarithmic mean temperature difference between T in and T out, and H is the heat exchange coefficient between the fluid and the room air. For water, H is around 10 watt per square meter Kelvin, while it is twice lower for air, meaning that the needed surface area when air is circulating is twice the one needed when water is circulated. Such a loss of space is not acceptable, and such air heat exchangers are never used. Such room air heat exchangers are never used in practice, as I just said. Instead, open systems are chosen. The duct is open and ends in the room, delivering the warm air which mixes with the room air and is exhausted back through a return pipe, exactly like with a mechanical supply and exhaust ventilation system, like this one. There is only one problem here, and that is that the volume flow rate of hygienic air is much lower than the flow rate needed to bring the heat or cold in the room. So the mechanical ventilation system must be much bigger and the ducts must be much larger, like that. So this has important consequences for the architect, who needs to reserve enough place for the ducts. Very often, mixed systems are used. The hygienic air is heated or cooled in an air handling unit, bringing this way a part of the needed heat and cold, and the remaining part is done by a water system. This saves a lot of space in the building. You see on the slide left a heating mode and right a cooling mode. Summarizing, you must make a difference between the transport of hygienic air and the transport of heat and cold. For the transport of hygienic air, 4 systems can be used, and only 2 of them, mechanical supply and exhaust, allow for preheating or pre-cooling of the air. In most cases, the flow rates of hygienic air are not enough to fully heat or cool a building. Heating and cooling can be done by a water system, bringing the needed heat and cold from the central generation system to each of the rooms. It can also be done by an air system, in which large quantities of warm or cold air are brought to each room. The ducts with such an air system are much larger than the ducts used in a water system. Very often, a mixed system is used, taking advantages of both. Thank you for listening. Goodbye.